Hello everyone, my name is Zhuxian Peng, and in this video I will introduce our CVPR work, Single Domain Generalization for crowd counting. So crowd counting is the task to count the number of people, mostly in an image. But in real-world applications of crowd counting, we encounter the domain shift problem. It means the distribution deviation from the training data, in other words, source domain, to unseen testing data, just the target domain. And we want to tackle domain shift with single domain generalization, which means that we generalize the models to any unobserved target domain using only data from a single source domain. However, while SDG has been well studied for classification and segmentation, most of the methods cannot be extended to crowd counting, a regression task without any category information used in those methods. Another unique challenge for SDG in crowd counting is called label ambiguity. Because density values in crowd counting are generated from point annotations, so human heads and backgrounds may be assigned to a similar value under different scenarios, and below is a very simple example of this phenomenon. DCCUS is the first work to consider domain generalization for crowd counting, but it is based on dividing the source domain into multiple subdomains, so it requires a rather broad source domain distribution. So our target is an SDG approach for crowd counting without such division, so that we can extend our methods to narrow source distribution. So we propose MPCount, a crowd counting method using memory bank and patchwise classification. It consists of mainly two parts: an attention memory bank to tackle density regression, and a patchwise classification to tackle label ambiguity. AMB covers continuous density values for regression and stores domain-invariant representation, and the content error mask eliminates domain-related content from info features for AMB, and attention consistency loss ensures the consistency of memory vectors in AMB. And another component, PC, mitigates the ambiguous pixel-level labels with coarser but more accurate information. So this is the overview of our MPCount. An image is first augmented so that we have two versions of images with the same content. They go to the VGG encoder and the decoder to form the feature, and the feature will go to the CEM to eliminate possible domain-related information. Then they are fed into the AMB for reconstruction, and then go to the density head for density regression. And in another branch, the deepest level of feature from the VGG encoder go to the PC head for patchwise classification prediction. And the entire progress is supervised by a combination of density losses, patchwise classification losses, and ACL. So let's discuss each component one by one. First, we have AMB. AMB reconstructs each feature vector as an attention over memory vectors. So any density value can be represented as a linear combination of representative values in the memory bank. And the CEM is based on the assumption that discrepancy of instance normalized feature reflects effects of domain shift on feature content. So we filter out such elements to ensure that AMB can learn domain-invariant information. ACL is based on our observation that features containing identical content information can have different attention distribution. So we want to ensure the similarity of these distributions to ensure that each memory vector is consistently updated toward the same direction. So lastly, we have patchwise classification. PC divides each image into patches of the same size, P times P, and each patch is classified into two classes containing human heads or not. So it provides a coarser but more accurate information than pixel-wise density maps. Okay, so let's see the results of our MPCount. MPCount beats state-of-the-art on traditional datasets like Shanghai Tech A, B, and UCF QRF. It even outperforms domain adaptation methods in some cases. And we also construct some domains with source domain distribution. And in such cases, our MPCount also outperforms all other methods. In the visualization results, you can see that there is no artifacts in the predictions of our MPCount that can be found in previous methods. Other visualizations also validate the effectiveness of our proposed components. We have also conducted a full set of evaluation studies, and here we show the study on model components. So in conclusion, MPCount addresses single-domain generalization for crowd counting with possibly narrow source distribution, with attention memory bank, content error mask, attention consistency loss, and patchwise classification. Extensive experiments show that MPCount achieves excellent results under different unseen scenarios and narrow source domain. So that's all for our video. If you have interest in our work, you can scan the QR code below to view our code and contact us. Thank you.